Oh, here we are, together again. How's it going, everyone? I'm John Haddad. I'm going to be talking today about the async Java profiler. Profiling Java applications specifically. This is a tool that I have used a lot over the last several years. Extremely helpful. Probably one of the best tools in observability that I've ever used. I was a big user of profilers back when I was at Netflix. We had some automated tooling that could generate flame graphs for us. We'll be talking a little bit about that. Just the absolute one of the best things I've ever used for just debugging Java performance. So yeah, let's just jump right into that. There we go. That's the one. Okay. So what are we looking at? First question, why profile? I think it's kind of important to go over this. Profiling gives you really detailed information as to what's going on in your system. There's a few people will sometimes talk about the pillars of observability. You never really hear profiling get mentioned in that. People are now talk a lot about distributed tracing, which is super popular with the OpenTelemetry library. You hear about metrics and you hear about logging, but you don't really hear a lot about profiling. But profiling is incredibly helpful when you're trying to understand what's going on a single machine. It's definitely not the tool that you're going to want to reach for to debug every problem that you have. But from a performance perspective, if you have like a service and the whole service is having performance problems, or you have a service in one node is having a problem, a lot of folks will just kind of throw things away and just launch a new node. And that's a decent, that's a fast workaround. There's pretty much no work to get going. But for me, like I work on Apache Cassandra a lot. That's what I did at Netflix. That's what I did at Apple. That's what I did for the last 10 plus years. And that's what I do now. As a consultant, I help folks a lot of the time figure out what their underlying performance problems are with Cassandra. And you can try and learn like every config that's in the system. I don't know them all. Most people don't know them all. Really, the best thing that you can do is to be curious, and be curious when you ask yourself, what is my program actually doing? A lot of the times people will think that it's a black box and you just kind of go, I don't know what it's doing. I'm not going to try and figure it out. Or I have some basic metrics, and you look at the underlying and you look at the metrics and they tell you a lot, but they don't tell you everything. And so I really like to reach for profiling more often than not, because I can match up what the underlying system is doing with the, my understanding of it. Look at the classes that are involved, figure out where the CPU is spending its time, and then I know what configuration settings I can optimize. So let's look into this in a little bit more. Right? As I said, we're taking the guesswork out of this. I want to know exactly where my time is spent. And for those of you that have looked at profilers before, if you've looked at like call grind or like cache grind or any of those profiling utilities that have been around forever, profiling isn't new. This has literally been around forever. You probably recognize this call tree view. This is an HTML version. It's pretty nice. It generates this tree view, and you can click on any of those pluses and minuses, and it expands the call tree, and you can see exactly where your time is spent. And this is awesome, right? This is really useful. I'm going to show you a little bit about how to use this in just a sec. So, hey, what's up, buddy? Good to see you too, man. I want to talk for a second though before we get into this about a sampling profiler. Sampling profilers are really, really cool. So you have a couple different ways that you can profile. You can either profile by looking at every single operation that a program is running, which gives you, um, you think it gives you accurate information, but the actual act of profiling has such high overhead that you don't really get to see the system in its like natural environment. It's like observing a tiger at the zoo, right? Like you don't really get an understanding of how a tiger behaves when you look at it, in a small enclosure, right? That's why a lot of zoos don't. Well, I mean, it's just not great for the animals. But you wouldn't get an understanding of how animals behave in the wild if you view them in a zoo. And it's just like that with profiling when you're trying to measure everything. So a lot of the best profilers these days are sampling profilers. So what this does is it essentially is a statistical method where we look occasionally at some frequency at what's going on in the running program, and we take a look at the stack, or we take a look at the heap, or we take a look at some aspect of it, and we basically take a bunch of snapshots of what's going on in the system, and then we aggregate it together, and we can get a pretty good idea of what's happening in your system. Really good idea to read a little bit more about sampling theory if you're interested in this. But for the sake of this discussion, I'm not going to get into the weeds on that. It's not necessary. So the thing that I really like about this is that this is designed to be safe to use in production. Whereas if you were to profile every single method invocation, uh, you you wouldn't be able to. It would just have too high of an overhead. But by using sampling, maybe we take a sample at like 99 hertz, and we're basically just like, okay, let's take a look. Let's take a look again. It means that we can see typically less than 1% overhead from introducing the profiler. So basically, we have this tool that allows us to kind of like take a peek under the hood at what our system is actually doing. We take a look at the classes, we see what's going on. You saw the profiler in that tree view before, and it can be incredible. You can get a lot of insight from it. The other thing that I really like about this async Java profiler is that it doesn't suffer from safe point bias. So safe point bias is really interesting. There's some profilers, the ones that do suffer from safe point bias, will effectively wait for the JVM to hit a safe point before they take a snapshot uh, of the stack and basically figure out what all the call times are. The problem with doing this is that there's certain operations that it can't stop in the middle of. So, for instance, if you do a memory map file operation, it won't stop in the middle, and there's certain loops that it won't stop in the middle. So save points can only occur. I mean, they can occur in a lot of places. They can occur in most places, but um, when you're looking at something like a database, you definitely, especially if that database is using mmap files, which by default Cassandra does, I really recommend using mmap index only if you're gonna be using Cassandra. But that's for a different discussion. Uh, when Where was I? When you're working, when you have a running system and it's doing I/O, you definitely do not want it to miss the the frames where it's in the middle of I/O. And so if you do have safe point bias, then you either have a safe point before or after or both, but never in the middle. And so the snapshot, the thing is that it's looking at the stack. So if you have to wait for the safe point, then you'll never register that mmap operation in your data set. So you have all this data, and it never says that it's in the middle of these I/O operations. And with the database, I/O is typically even with NVMe, you end up spending a lot of time in I/O. So like on a standard solid state drive, if you have a page cache miss, you're going to be waiting for like 2 or 3 milliseconds. And if you're working with a like EBS, for example, um, the performance can vary depending on the number of provisioned IOPS that you have um, and the throughput that you've set things to. In fact, next week I'm going to be talking about how we can look at EBS and understand its performance a little bit better using FIO. So if that's an interesting topic, then you'll definitely want to come back next week and check that out. But anyway, moving on. So I'm going to jump right now into a few examples of what this is going to look like. This is going to be just a heads up. This is going to be a shorter stream than some of the ones I've done in the past. I don't necessarily feel like I need to fill out like an hour. I think that this tool is, with a few examples, it'll be pretty obvious kind of what the advantages are of using this tool over like guessing or just trying to figure things out through like logic or reading the code. I've actually figured out a lot of my underlying knowledge in Cassandra comes from working with profilers. So with the async-profiler, I look at what's going on in my call stack, and then I will match it up to the code. So that's how I actually got started in the Cassandra code base. So let's take a look at what this looks like. If we're going to get a profile, it looks like this. So there used to be a script that would just be called like profile.sh, and now it's a little bit nicer. There's actually a utility called asprof that comes with the async profiler. And if you're interested in getting the async profiler, I have a link in the description of this video. There's, in fact, the link to the description has not only the async profiler linked, but it has a blog post that I wrote of a topic that some of this material I cover over there. Not all of it. Some of the stuff in here is new. But if you're interested in kind of like getting these commands and figuring out how this stuff runs, you can either use the blog post or you can use the README for the repo, because there's a lot of really good information in there. Anyway, what we have here is a CPU flame graph. I explicitly have called this out with the -E. You don't really need it. If you don't specify -E CPU, it assumes it by default because that's what most people are going to use. So this is looking at CPU timing and figuring out like where your time is spent. And then you can also see that I have this -F flag where it goes to temp/flamegraph cpu.html. Now I haven't talked about flame graphs yet. I only showed you the call tree. Flame graphs are a really, really interesting visualization. So if you are kind of curious as to like what's going on in your system, flame graphs are really nice because they give you this like holistic view as to what's going on. When you go up and down, that's the stack. So that's actually your call stack. So if you were to like look at the top, you could see, hopefully you can see it. It says LZ4 decompress. That means and it's kind of wide. The width indicates the amount of time that is spent in this portion of the stack. So the fatter the area of the graph, the more time is spent there. So the reason why I like this is because it makes it really easy to just kind of like, you just look at it and you're like, oh, this thing is wide. That's where I'm spending my time. And a lot of the times, like I'm gonna, this is a graph of a running Cassandra node. A lot of the time that I do this, I actually see this exact type of thing. At the top, you see LZ4 decompress. And the reason for that is because prior to Cassandra 4.0, we used compression settings that were optimized for to compress more data, assuming that you're doing larger reads. But if you're doing small reads, like if you have counters or lightweight transactions, or you're just doing super small reads, you would be decompressing a lot more data than you need to. And so Cassandra would actually spend a lot of time on the CPU just decompressing data, even if you didn't need it. And the downside here is that you end up with a lot of read amplification because you're pulling more data off disk, you're pulling more data into the JVM, and you're decompressing more data. So this is the easiest way to spot where your system is taking performance wise, or where your system is spending its time performance wise. It's why when people say, when I talk to teams, I always ask for this. A lot of the times, I've worked with several teams that have described their workloads to me, and they say our reads are slow, or they'll more usually they'll say my writes are slow, or we're seeing long GC pauses. What do we do? And the thing is that I think a lot of people have that kind of old adage about like going to the doctor and you say, "Hey, my knee hurts," and or my it hurts when I do this, right? And the doctor goes, "Well, stop doing that." And so a lot of folks will assume that, with the database, it's a similar thing. It's this is slow, and so I like X is slow, and so I need to make X faster. But what people don't really take into account is that there's a lot of other stuff happening. Like again, with Cassandra, you've got the overhead for reads, you've got the overhead for writes, and if you're seeing slow writes, like writes are fairly simple from a resource perspective. You can do a lot more writes than you can do reads, and so people will say, "Hey, I've got I've got the system, and my reads are, or sorry, my writes are really slow. How can we tune writes?" And that's often the wrong approach. You generally speaking, you do not want to come at this and say, "How do I tune the thing that's slow?" What you want to do is you want to look at your system as a whole and evaluate where the machine is spending CPU time, where the machine is spending time in IO. And a lot of the times, like I said, you'll see either compaction or repair or just reads in general. And so what happens is that when you tune reads, your writes get faster because if you free up CPU, then you no longer have contention between the two operations that you're doing. If all of a sudden you make your reads 10 times faster and take, a tenth of the resources that they did before, then your writes are also going to naturally get faster because they're no longer competing for the CPU that may be completely busy. So it's a good idea to use flame graphs and use profilers to understand where the time is being spent. There's a few other options that we can use with flame graphs that I find really useful. There's this reverse option. You can pass -- reverse. You can also call it an isograph, I believe. So Brendan Gregg is an ex Netflix guy that he's the one that came up with flame graphs, and he's written a lot of performance tools. And he didn't write the async profiler. The async profiler is written by other people. But the concepts are all kind of universal and they're applied everywhere because they're so useful and so good that like you can't have flame graphs, a good flame graph system without having isagraphs as well. And isagraphs are really interesting because they basically show you, instead of starting at the bottom of the stack and working up, they show you the top of the stack and work down. So if you have let's suppose at the top of the stack, you have some function calls that are being used in a lot of different code paths. It's really hard to understand how much time they're really taking, because if they take 3% of the CPU and there's like 10 spikes, you only see, in each spike, you would only see them like come up into this like small tip in the top of the graph. But really, if they're using 30% of the CPU, you would have no way of knowing that. And so what you do with an icicle graph is it shows you the top where that function call is taking up 30% of your CPU time, and then it splits out the stack going back to the bottom. So icicle graphs are really useful for for those times where your running system has those cases where there's code paths that get hit by multiple different like areas of the process. Like a good example, again, on the Cassandra side, is like reading an SS table. reading an SS table can be done through a regular compaction. It can be done through a repair. It can be done through a regular read. It can be done. It gets hit in the lightweight transaction path. It gets hit in the counter path. There's all these different ways that it can be arrived at, but they don't start at the same exact base. And so as the graph gets built up, you kind of lose some of that information. So icicle graphs are really nice for getting to the bottom of that sort of thing. We also have the option to do Java method profiling. Java method profiling is pretty cool too. So if you've narrowed down, or you're just curious as to like where, what is going on with a particular class and method, this is particularly useful. So let's suppose that you've already identified that something is a problem based on the graphs, but maybe you want to draw another graph and cut out some of the noise. It's not uncommon where you'd want to take multiple flame graphs, or you'd want to kind of like go through multiple cycles. And so if you make a change, like let's suppose you change compaction throughput, right? So if you change compaction throughput and you want to, or really, again, let's come back to the compression chunk length. If you change those types of settings and you want to see what the difference is, but you want to isolate part of the code, you can do that. So if you pass this -E again, but instead of passing CPU or any of the other options, you can literally pass a class and a method, and unfortunately I've like I've named this thing weird. You can see it says temp flame graph query processor. Ignore that. This should just say write unsigned vint. But I took a flame graph and I just kind of wanted to look at this one thing. And so what's nice is that it kind of isolates part of the code. It will allow you to see what this like one block of code is doing, and it goes all the way up to the thing that I mentioned, and it will actually trace every invocation of that. So if you have one thing that you're like really, really curious about, this is a good way of figuring it out. Another option, and this is also incredibly useful, is heap profiling. And this might not be super obvious, but I'm just going to show you real quick what this looks like. Heap profiling is really cool. So there are a number of cases where you're going to want to rely on heap profiling. I'm going to talk about them in just a moment. But this is essentially the same visualization applied to allocations, as I had already talked about with the CPU side of things. So when stuff is allocated in the JVM, that determines the width. The more stuff you get allocated, the larger the larger the bar, right? This is incredibly useful, and it may not be obvious why. Here's another example of a profile that I took. So the first example that I had, I took when I was doing really small writes, or I think it was actually a mixed workload of reads and writes. So small reads and writes give us this, right? Lots of stuff happening. The time is kind of distributed all over the place. But when I started to use really big values, and when I say really big, I don't even mean like that big. Like this was either 100K or like 1 meg or something like that. This was kind of like a test to prove a point. What we see at the top here is you see those byte arrays, and they're huge. They absolutely dominate the allocations. Now, the reason why I care about this, right? Like, why do we even care about heap profiling? Heap profiling helps us identify the root cause of GC pauses. So I'm just going to talk about GC pauses for a minute here, because I think that a lot of folks still don't kind of understand GC pauses. And I think a lot of people want to write software in a way that kind of like uses the JVM as a crutch and kind of ignores the benefits of being stingy with your allocations. Here's the thing about the JVM, and this is true no matter what the JVM. There is no way around this. More allocations are going to lead to more pauses because the JVM has a finite amount of memory. Uh, there are no, there is no infinite memory systems. There are definitely folks that run JVMs, especially nowadays, on like really huge, uh, boxes with a ton of RAM, and that's cool. But you still have to be careful about the amount of allocation that you do. The the other thing is that, and a lot of the work that can be done with modern JVMs, some of that stuff gets done in the background, but the work still has to be done, right? So you're still spending time. You're still burning CPU, copying memory around, updating pointers. Like it's not free or even cheap. If you over allocate in the JVM, what ends up happening is you see a ton of pauses. And if GC can't keep up with your pauses, everything slows down. Like the JVM literally has to pause everything. Even with the newer algorithms like ZGC, Shenandoah, um, there's no way of, like, your GC has to keep up with your allocations. That's the that's like the main thing. So if you allocate faster than your garbage collector can catch up, eventually you are going to have a super long pause where your heap is completely full and things just fall apart. So a lot of GC tuning is really about trying to, especially with older systems where you might be relying on Parnu and CMS, you would be kind of like trying to figure out, like, do you have a lot of long-lived objects or short-lived objects, and then you're trying to kind of tune your new gen so that it can be big enough. Like if you have a lot of short-lived objects, you want a huge new gen so that like you have more time in between pauses and the objects can die, and then they don't get promoted. But at the end of the day, like, it doesn't matter what your algorithm is, you're always going to have better performance if you don't do unnecessary allocations. And so by using those that heat profile, like I was showing you over here, you can see that there's only a few spots where these allocations occur. And this was actually the beginning of an investigation that will hopefully yield uh, performance improvements in Cassandra down the line, using larger objects. Because right now, if you put like a 1 meg value in, we actually do, because we do so much allocation, what ends up happening is you hit frequent GC pauses. And so if we could like reuse if we could reuse byte buffers instead of allocating new ones, we'd actually be able um, to reduce the overhead of using large objects. And as you can see, there's only a few locations where this is even really a problem. So if we can fix 1, 2, 3, 4, 5 locations where these like huge allocations are being done, then we could end up with large objects working much better in Cassandra. I still wouldn't recommend doing huge ones because there's some stuff with the commit log, and there's some funny business there. It's not designed for it, but it could be better. And like, if we can make the system better for more people, then we're going to be pretty happy about that. Um, so that brings me to the end. Um, Only half an hour today, it looks like. We'll wrap it up. Next week, I'm going to be talking about how to benchmark EBS, in particular GP3, using FIO. This is a pretty interesting topic to me. I've run a lot of databases in Amazon. I've worked on a few as a consultant over the years, a few hundred or a couple hundred probably clusters that have been in Amazon. And then in the last year, I've worked on some Amazon stuff as well. And one of the things that I kind of want to get a little bit more insight into is the underlying performance of EBS. So I'm going to be doing that research. I'm going to be figuring out what's going on. and I'm going to be sharing it. I'm going to be discussing my results in the stream. So yeah, that wraps this up. It looks like there's no questions. So thanks very much for checking this out. If you are interested in working with me and getting some help, especially around performance, reach out. And if you are a Cassandra operator and you're looking to level up your game, I am starting a training program, and that the first class is going to be kicking off at the beginning of April. So that's in the description as well. Go to rustyrazorblade.com/training. You can check that out. You're going to learn a lot. This is meant to help people go from the common case operator to pro level. And then it's definitely and it's based on the work that I've done. I mentioned I've been doing this for over 10 years now. My work at Netflix, my work at Apple, my work consulting, my work putting Cassandra in production. So this is kind of what I've been living and breathing for a while, and I'm looking to help everybody become professional, become top experts. So, all right. Thank you very much, everyone. Appreciate you stopping by, and I'll see you next week.